Okay, so this is probably the only non-technical talk at this conference as far as I can tell. And really what we're talking about is enabling new users. So for those of you in the audience that are at an educational facility or have data scientists that you want to enable in a different way, this is kind of your talk. What we're going to talk about today is a hackathon that we did in the spring. We're going to talk through some of the format things that we did that were a little bit different. And then in that context, I'm going to introduce something called Open OnDemand to you guys, which is really the enabler here. So this is the event. It's a little bit out of focus. That's my fault. But you know, I guess we'll talk about all the details here in a few minutes, but this is something that we ran this last spring. We had about 52 people register. And we'll talk about the format and what we did later. So this is really the agenda. I'm going to talk kind of fast since we're already 10 minutes late. But anyhow, so what I'm going to do is introduce ARC at VT. For those of you that don't know us, talk about the hackathon, talk a bit about the barriers to HPC as I see it, introduce something called Open OnDemand, which is the enabler that I was talking about. And then we'll talk about some of the hackathon projects. So who are we? So ARC at Virginia Tech. Basically, we're a unit within IT that is responsible for making sure that users or people at Virginia Tech have access to compute appropriate for the size and scale of their projects. Just a little bit about VT. That's kind of our user base right there. The blue is engineering. We're largely an engineering university. Yellow is College of Science, and then we've got sort of everybody else. And so that's what we'll talk about a little bit later. In terms of what do we have at Virginia Tech, we have about 1,000 total nodes of compute. Most of them are x86, is probably the case just about everywhere, but we have these 14 Power 8 nodes that have quite a bit of power to them. And that's really the topic of this hackathon, is how do we use that. I'm one of about 5 computational scientists within ARC, and my job is really to enable people at Tech to use our systems. Sometimes that means just showing people where to log in. Sometimes that means helping people find software. Sometimes that means educating. And so hackathons kind of fall into that education component as I see it. So here's the event again. Basically what we did is we had a 2-week hackathon. So we met once on a Friday, and Clarice came out and gave a nice presentation. And then we met again in 2 weeks where basically people presented their solutions, and we'll talk about the solutions later. The goal was really to accelerate a model. That was it. It was pretty simple. Take something that is on an x86 machine, for instance, and then put it onto Power and see how much faster Power is. And so that was really the goal. So we made it pretty simple because we wanted to really bring people to the Power ecosystem, and many of the people weren't very familiar with it. So that's the goal. So primary goal, demonstrate optimizing training time can impact time to results. That's kind of obvious. And the second is sort of what you'd expect from a hackathon. So bring together students from different disciplines and just kind of mix them and see what they do. So that's kind of the fun part for me. In any hackathon, there has to be a goal. Okay, so the deliverables in this case were really 5 to 10 minute presentations. I think they all ended up being 15 to 20, but that's okay. Some code, so we have some Python Jupyter notebooks. And then ultimately what we were asking people to do was put together white papers that IBM could use or OpenPOWER, I guess, could use to advertise what can be done on their system. Importantly, at Virginia Tech, we're a pretty spread out university. So we use Slack for communication, which was pretty cool. So 2 things that were cool about this. One, we were able to get the IBM developers, I guess, onto Slack. So they were able to actively answer questions. The computational scientists were all involved, but then we also had students from different locations within Virginia Tech. So we're spread out all over the state of Virginia, and so we had people at least an hour away that were participating in teams that were, I guess, distributed. So that was pretty cool. We have to evaluate the submissions. Here's the criteria. It doesn't really matter, but really, what we're trying to focus on was how do people use the Power system, and what's the potential impact or benefit of what they've done. Creativity was kind of the fun part for me, to see what kind of diverse solutions people put together. And just kind of continuing down this, we had about 52 people, as I mentioned. We had people from all over campus, so biology, statistics, computer science, engineering, medicine, even plant pathology. So we had a very diverse set of people joining us. Many of the people, when we polled them, said that they're familiar with AI or deep learning. Nobody really said experts, okay? So what that means is that as hosts to the hackathon, we have to do something to sort of bring these people up and allow them to be creative and be good participants. Almost none of them had HPC experience, okay? So thinking back to the goal of this hackathon, it's deep learning, it's PowerAI, it's that type of stuff. It's not teach people HPC. And so for the couple of people here that teach classes, you'll know that getting people onto HPC and understanding how to submit jobs and that type of stuff can be a pretty arduous task, okay? So for instance, many of the people in biology or plant pathology might not live at the command line. They're in the lab, right? So we need to figure out how to enable them to participate without spending all of our time teaching them Linux and HPC. So, coming back to this, hardware is really not our issue. It's really access and use. And in my opinion, these are largely self-imposed. So thinking about the blue part of the curve over there, those are engineers. They're good to go. Most of them have already been taught SSH and command line access and Linux and that type of stuff. We're really speaking to the other half that are more focusing on how do they perform experiments, what are they doing in the lab, and that type of stuff. So barriers, how do you get into the system? Traditionally, it's SSH. Software, how do you install software? There's no root access, so software installs are often hard. People aren't familiar with modules, which is how we handle our software on the ARC systems. The data's not in our systems to start with, so we have to teach people FTP, SCP, et cetera. Script writing is not a native tongue for many people, so something needs to be done there. And then job scheduling. People aren't familiar in some of these disciplines with scheduling jobs. You press run and it just kind of goes. So this is where Open OnDemand comes in. So Open OnDemand is really a system for accessing HPC through web-based GUI. So what's cool is what we're doing is we're exposing our systems through tools that people already know. So it's a plug-in-free web experience, meaning that you just open a web browser and it works. We're going to provide file management apps, a way to get into the command line that's a little easier than installing PuTTY or Moab or whatever. A way to look at jobs, and then some graphical environments for people to sort of look at what they're doing. So out of the box, what do you get? Basically, some sort of landing page that you can customize to the site's liking. So I'm showing you the Ohio Supercomputer Center's landing page. Ours looks different. there's a Files app, there's a Job Composer app, and there's a job Monitor. Those are sort of the basic things. Going through them sort of one at a time, just real quick. Files app basically looks like what you'd expect from a web-based files manager. So what's cool here is that basically we don't have to SCP, at least sort of medium-ish files. So we can just drag and drop. We're beyond SCP, we're beyond FTP. For many people, this is great. Incidentally, the last thing there is pretty important. You know, there's a lot of people that'll write down in their scripts RM minus RF, and maybe there's a star in there. True story, one of our bigger users just did that and lost 50 terabytes of data right before we're migrating to a new storage system, so that's not all bad from my perspective, but you know, I mean, this is a big deal. So for many people, command line manipulation of files is completely new, okay? And so having some way for people to play with files in a more familiar way is important. A pretty common workflow for many people is going to be to start a job. Well, first you have to write a script, then you submit a job, then you see that it's running, and then you get the results back. We can put a GUI around that. That's what we've done here. This is the Job Composer app. We're not going to focus on that today, but this is a pretty cool tool. This is the thing that I want to bring people to. So we can extend the interface. So we can write what are called apps that are custom around various things that you might want to do. So for instance, Jupyter Notebooks, which is what we're going to use in the hackathon. One of the way to get a Jupyter Notebook on our systems is submit a job, create some sort of SSH tunnel, open up Jupyter Notebook, and hit it on your browser. For someone that's not familiar with HPC, setting up tunnels and that type of stuff is like, so we need some better way to do that. Same goes for MATLAB. Traditionally, we don't have GUI type systems on our compute nodes for security reasons, but we can abstract some of the starting of some of these GUIs and allow some of these various apps to run. So it is pretty easy to facilitate or to extend and write these apps. The documentation is really well built out, and developing apps is pretty fast and easy. So here's a list of apps that I put together in about a day, I guess. There's some nice templates online. So, coming back to where we're going here. So one of the things that my group is responsible for is going out and teaching like intro to HPC, okay? Oftentimes we'll do that in a classroom setting, and we'll go into, a group of 30 to 50 students, and we'll spend probably 40 minutes trying to get people to install PuTTY or whatever their platform-specific shell client is, and then get SSH'd into the clusters. What we're doing here with Open OnDemand is we're authenticating people into the browser, so that's kind of done. We know who they are. And then they simply click on a little button that opens up the shell. So we've taken what did take 40 minutes for a class to less than 15 minutes or so. So in other words, we have more time to actually talk about compute versus just get into the damn system. So pretty radical idea. For us, what we wanted to do was really get them into not necessarily the shell app, but rather into some environments more specific to the IBM ecosystem, so the PowerAI toolset. So we had about 50 participants. We had about 2 weeks, so we could have spent a lot of time, teaching HPC and stuff. Instead, what we wanted to do was use Open OnDemand as really the portal to get into the system. So what we did is we created a Jupyter Notebook app and a TensorFlow app, but basically the Jupyter Notebook app by default loaded the PowerAI toolset. So users click on a little button, loads the Jupyter Notebook, pops up in their browser, and it has the environment all set up. So in basically one click, users are into PowerAI, a PowerAI Conda environment. TensorFlow is kind of the same way. So I'd say for probably 3 months when we got the PowerAI system up and running, people would often come into our offices and kind of spend a bunch of time trying to figure out how to get the tensor board working. So what we've done here is it's now just an app. All you do is you specify the directory where your TensorFlow logs are, and you start the app, and it pops up the tensor board. So pretty nice. Okay. So anytime you give users or students, I guess, a chance to be creative, they'll take it. The first thing that we did is we said, well, create yourself some teams and give yourself a team name. And so you can see some of the fun ones that came up here. I was expecting Gannison to be here. One of the ones that he really liked is the Chennai Super Kings. I guess it's some sort of cricket team in India or something, but anyhow, kind of fun. So to the hackathon, we had basically 3 finalist teams, and I wanted to just show you quickly the solutions that they came up with. These solutions were very diverse in terms of topics. So we went from game AI to cell type classification, and then GANs for creating data sets in CFD. And so we'll go through those here in a second. So the first team, like a Gauss, turns out that one of the 2 members is in our School of Medicine, and he works in an NMR or MRI lab. And so that's where the name comes from, I guess. But anyhow, they were interested, they were brand new to deep learning, okay? So for whatever reason, they were really interested in reinforcement learning. Their particular app was Pong, not that difficult. But Elon, in this particular case, was interested more in terms of what he could do in image processing. And Veron was more interested in terms of what he could do with reinforcement learning for robot manipulation. Diverse things, but they kind of came together around this project here. So what they're going to do is they're going to take this actor-critic algorithm that's traditionally CPU, and they're going to port it to, or they're just showing acceleration on a GPU version of that. So what does PowerAI get them? So the scale is a little bit blurry, but in the first case, we're getting to a max score on Atari in about 10 hours, and we went down to about 150 minutes. So a pretty dramatic improvement. The second team is, they came out of the biological sciences, and they were interested in something completely different. So their application is around DNA sequencing, specifically in tumors is where their interest was. And what they're wanting to do is show that if you go from a bulk analysis to an analysis on the DNA sequencing side where you're sequencing single cells, you can use the DNA profiles or RNA profiles in this case to determine which cell type that is. So for instance, if you get a tissue biopsy, there's probably going to be some normal cells in there, there's going to be some cancerous cells in there. Can you use the RNA profile signature to determine which of those two it is first before you do any other analysis. So they're using a pretty complex algorithm. This is called the Siamese neural network, where basically they're taking 2 samples through the network at the same time, and through some mechanisms I'm not sure I really understand, they kind of mix the results from the networks and then come out with sort of a mixed signal at the end. And so they run them through at the same time. So in the first 2 cases, I'm showing positive pairs, or they're showing positive pairs. In the second case, it's a negative pair. So in other words, the cell types are the same or they're different. In their case, they had a problem in that their data was so large they could not run even a significant portion of their data through a GPU at one time. So what they were really looking at is how can they speed this up using some sort of distributed learning. Okay, so they want to take their data, spread it over multiple GPUs and push it through faster, and then look at the accuracy. Their results were basically what you would expect. Accuracy is pretty constant. Okay, so it's a little blurry, but it's in the far set of histograms. It's a constant accuracy. When they change to a different network, so the Siamese neural network, you can see that they have better accuracy than sort of what they would use traditionally. Interestingly enough, as they scaled to more GPUs, accuracy went down. I don't think they understand what that is. And then these curves here are really sort of training time as they scale to multiple nodes and GPUs. And so, as you would hope, the training time goes down as you scale across more and more nodes and GPUs. It's not linear, and you know, I think they got what they hoped for. So the last application is GANs for CFD. So what these guys are out of our engineering department. What they're looking at is airflow across various airfoils. So for instance, across the wing, across the fuselage, etc. As you might imagine, getting these data sets is pretty expensive. And so if there's a way for them to generate data sets, that would be advantageous if they could use that to augment data. So I'm not going to go through this, but basically they've got a loss function at the bottom. That's really what you need to do some sort of deep learning algorithm, is you've got a loss to measure how good you did, so you can do some updates. And what they're doing is they're programming in the physics, right? So you've got some data, or so in this case your data is up top in the red here. And what you're doing is you're setting up sort of a generator and a discriminator, and they're going to maximize the discriminator's power, but they're going to minimize the generator's loss, is effectively the way it goes. So all this stuff is in a white paper that we'll I guess post. So I don't need to go through this, but here's another sort of way to think about this. They've got the physical equations here, and they've got constraints, and they can set that up and use this in this generative fashion. Sort of early on, what they were showing us is how well their generated data looks compared to what their actual data looks like. So the top here is actual data, there's generated data, and what they're showing is that the generated data starts to look more and more like actual data, and that's what you would hope. In their particular case, they had a lot of parameters that they were interested in exploring. So I don't need to go through it all here, but they have a pretty complex system that they're playing with. They have a lot of considerations. Probably the biggest here for them was scalability, which pretty quickly gets to latency. So they've got multiple neural networks running at the same time, and they need to talk across ultimately nodes. Measures of convergence, and their little note here is that their divergence is their convergence metric. But what they're really looking for is GANs are inherently difficult to get to train and converge. And so how long does it take, and how many nodes and GPUs can they use to get to trained networks? At the end of the day, we get to here, which is basically using the PowerAI system or the Power 8 systems with PowerAI to get their models to converge, and looking at the training times for the different numbers of GPUs. They have this, the red and the blue bars are really using GPUs on the same node versus intranode, and controlling, or I guess shifting who the controlling GPU is. It's kind of a fun project. So really, just to summarize, we put together this hackathon. Its target was really people that were new to our system. We had a really a different way to do this, in that we spread this out over time. Okay, so this wasn't a 24 or 48 hour sprint. It was really get intimate with the system over a couple of weeks. We use some communication tools to really help both us support them and them to communicate. We used Open OnDemand really to level the playing field, to make it a little bit easier for new users to use our systems, so they got up to speed faster. And then ultimately our topic was bring your own model and just show that it accelerates, which I think allowed for more different types of models across many different fields, which was really cool. And that's it. Thoughts or questions? Yeah.
I have a technical question you may not know the answer to, but I figured I'd ask. You mentioned that you had a browser-based experience, but you could launch a shell from that.
Yeah.
Which shell, and what was the technology for getting a shell environment pumped through a browser, which smells like a Java applet to me, but...
It is not a Java applet, and I don't know which shell that they use, but I can get the answer to you.
Okay. Yeah.
Sorry?
I think it's Node.js.
Is it? Yeah. Do you guys use Open OnDemand? Yeah.
I was going to ask you if you had problems with authentication, having to re-authenticate different parts of the service.
I don't. We've had this going for, well, I guess since the beginning of the year, and we have not seen that as an issue.
We've been working for several years, and we have one version that has problems every single time we put it on the FTP, we should re-authenticate. That added this barrier to our teachers and our users when this stuff does.
Yeah. We are two-factor, and we didn't have any issues with that. We're on version 1.4. We are.
IPA, or is it?
I'm not sure. Yeah. Yep.
What was the interconnect? Think about the last use case. The interconnect between the compute nodes?
It's IB.
Oh, it is IB?
Mm-hmm.
Okay. Because typically what you see is when you have problems with your, going to multiple GPUs across multiple nodes, if the connection is slow, so IB would be really...
Yeah. And their data set size was, so you're thinking specifically the bio app? CFD?
The CFD, yeah. Yeah, that chart right there, right?
Yeah.
It doesn't make a lot of sense.
That doesn't make a lot of sense. Were they using, I wouldn't know the weeds, but were they using Orabot, or were they just using NPI, or do you know?
They were using MPI, and this was the power version of MPI.
Okay, so the
I'll mention
Orabot.
the Open MPI was compiled in and it worked on the AC 922, they just don't know how it works.
Yeah, that's what it is.
Maybe.
Because usually, that shouldn't make any difference. I mean, your accuracy may be different because of the way whether you're going synchronous or asynchronous compression
Mhm.
models, but that shouldn't.
That should exceed.
Yeah, that should.
Yeah, no, I mean, we should probably have them redo this because, well, I guess it's been about a month or so ago, one of our computational scientists put a lot of effort into MPI and specifically getting MVPitch compiled right on our systems. So this might be changed.
Getting what version of MPI? That's just that last thing again.
This was OpenMPI, it was probably 3, but I'd have to, you know, it's the version that comes, that ships with this was PowerAI 1.6. So, you know, that comes with an MPI. Yeah.
It's community edition or non-community edition?
This was Community Edition. Okay, thank you very much.